Okay. Welcome everybody to today. We have Wen-Yuan Ai from King's College in London, and he will be talking about PT-symmetric minus, very important, G5 to the 4 theory. So when you're ready, please go ahead.
Yeah, and first of all, I would like to thank the organizers, Andreas and Francisco, for providing me this excellent chance to present our work here. And today I'm going to talk about the PT-symmetric. So the PT-symmetric minus G5 theory, and this talk. So why is always something like okay. So today I'm going. This talk is based on a work done together with Bender and Sabansaka. Wait, why? Okay. So this is the outline of this talk. I will start with some motivations, and then I will give a very brief review of the PT-symmetric minus G5 quantum mechanic problem. After that, then I will discuss the path integral formulation of this theory, and there I will try to propose a relation between the PT-symmetric minus G5 theory and Hermitian theory with a positive quartic potential. Then we will discuss this relation in a Toyer model in zero-dimensional space-time, and then discuss the quantum mechanical problem. Finally, I will give my conclusions. So let me start with the motivations. The first question is why PT-symmetric theories are interesting. Very simply, this is just because PT-symmetric theories are becoming more and more important and have attracted more and more attention. And I think this is from my understanding, this is the first paper on the Hermitian PT-symmetric theory. And then you can see that the paper has been cited over 6,000 times. And from the last year, it has been cited over 700 times. Okay. But more specifically, PT-symmetric theories are interesting because they are actually extensions of the Hermitian quantum mechanics. Actually, they are a kind of complex extensions, and then therefore we have more possibilities in application. And we know that in the past decade, there have been a lot of developments in condensed matter physics related to non-Hermitian materials. And because of the first point, PT-symmetric theories also have very rich theoretical structure. Now here we can have Stokes phenomena, topological picture of quantization, and PT phase transition, asymptotic analysis, and many more. Now also PT-symmetric theories could be a new avenue to beyond the standard model. And we know that the standard model of particle physics cannot be complete. There are many problems that the standard model cannot explain. For example, what is dark matter? What is dark energy? And why there are neutrino oscillations? What are the solutions to the strong speed problem, to the hierarchy problem, so on and so forth? In recent years, some authors try to resolve these problems with PT-symmetric quantum field theories. But actually, there are still many questions that have not been answered in PT-symmetric theories. Here, I will mention three. For example, from my understanding, I still do not see a first principle derivation of path integral formulation of PT-symmetric theories. I will explain this later. And also PT-symmetric QFTs remain to be largely undeveloped. And at last, we still do not see a clear relation between a non-Hermitian PT-symmetric theory and another Hermitian series. Of course, we know that for certain Hermitian quantum mechanics, there's a kind of map between between non-Hermitian PT-symmetric theory to Hermitian theory. But here, actually, what I want to ask is that, can we actually obtain a non-Hermitian PT-symmetric theory from another Hermitian theory via analytic continuation? And the target of this talk is to give a preliminary attempt to the above questions using the very simple -G54 theory. Now, let me review the PT-symmetric -G54 theory. We start with this Lagrangian. And in the potential, we have a maston, positive maston, but a negative quartic potential. The potential looks like this. So in the Hermitian framework, this potential does not have a ground state, a stable ground state. And therefore, this theory is thought to be ill-defined in the Hermitian framework. However, in the non-Hermitian framework, actually, this theory has a real and a positive energy spectrum. To implement this, we need to allow X here to take complex values. But this does not mean that we introduce additional degree of freedom. We still have 1 degree of freedom, but we just deform the X from the real line to a contour in the complex plane. There are 2 ways to understand why this theory can have a real and a positive energy spectrum. First, we can understand this from the Born-Sommerfeld quantization. Once we allow X to take complex values, and we can then look at the classical motions of this particle in this potential. Now, this plot is taken from this book, PT-symmetry, and this plot is only for massless case. But we can see that the trajectories of this particle are closed. And therefore, we can apply the formula, the Born-Sommerfeld quantization formula, to obtain approximately the energy eigenvalues. On the other hand, we can also solve the time-independent Schrödinger equation directly. Here you can see that we need to deform the contour, the real line to a contour in the complex plane. And you have to choose the Stokes wedges in a PT-symmetric way, okay? And this is called eigenfunction contour. And yeah, and if you solve the equation, then you can obtain real and positive eigenvalues. Well, this is -G54 quantum mechanic problem. But what if we consider a -G54 quantum field theory? And I think this theory still is not well understood, because now we have infinity degrees of freedom. For example, what is Hilbert space? And what about renormalization? I just want to mention by passing actually 2 papers discussing the renormalization properties for this theory. And now, with quantum field theory, the Schrödinger equation is now of functional form. This is originally we just have an ordinary equation, differential equation, but now this equation is much more difficult to solve, if not impossible. So we need to search for new approaches, and the new approach we are going to use is the path integral. The path integral is actually a standard tool in quantum mechanics and quantum field theory. But for PT-symmetric theory, it is less used compared to the Schrödinger equation. Why do we need to use path integral? Because in the path integral formulation of quantum mechanics and quantum field theory, actually there's no big difference between quantum mechanics problem and quantum field theory. Now, let me briefly review how we obtain the path integral formulation for Hermitian theory. So usually we start with a propagator. This is our propagator. We start with an initial position xi and to a final state position xf. And then we can divide the total time t into n pieces, with each piece being very, very small. Finally, we need to take n to infinity. Then the evolution operator, the time evolution operator can be written as a product of many time evolution with small time, delta t. And then you can insert the completeness relation into this propagator. Then finally, the propagator, the original propagator can be written as a product. Now you still need to evaluate xj to xj plus 1. Then to do that, you can further use the completeness relation for the momentum eigenstates, and also use the inner product between the momentum eigenstates and the position eigenstates. And of course, they are complex conjugates. So in conclusion, to derive the path integral from first principles, we actually need to know inner products in the theory. And this is very difficult for PT-symmetric theories, usually. I'm not sure it is possible for -G5 theory, because I'm actually not very familiar with C operator in for PT series and CPT product in the product actually. But in our work, actually, we use the following assumption: path integral for a theory. So either Hermitian or non-Hermitian PT-symmetric. They can be described by this formula. And this is XE is the ordinary Euclidean action. But now we actually consider some contour C, and C is not necessarily the real functional space. So the C has to satisfy two conditions. The first one, it must ensure the convergence of the integral, and the second, it needs to satisfy the PT-symmetry. And actually, the second condition is very difficult to analyze, but we will determine the contour using the semi-classical methods. Right. By the way, so you can interrupt me anytime if you have any questions or confusions. Now we have two theories. The first one is Hermitian theory, the ordinary lambda x4 theory. And then the contour C is real functional space. We denote the partition function as the Hermitian of lambda. Also, we have a non-Hermitian PT-symmetric theory with a negative quadratic potential. But now, the contour C must be a certain deformed functional space. And we denote the partition function as the PT of G. Now, our question is there any relation between these two partition functions? To answer this question, we have to first look into the structure of the Hermitian theory. And the Hermitian theory is usually studied by the perturbation theory. Here, I take the energy function as example. And then you just have perturbative series. You can expand E of lambda as A0 plus A1 lambda, so on and so forth. It turns out that
Wen-Yuan, can I just make a brief comment?
Yeah, sure.
Yeah, so the negative quartic theory is actually an extremely interesting, and well, I should say unique theory, because although it is really non-trivial, there is this connection in quantum mechanics, in the case of one-dimensional quantum field theory. There is this connection between the Hermitian theory and the non-Hermitian theory. There's a mapping, and therefore, in principle, we sort of know what the C operator is in some sort of closed form. However, this is a very non-trivial problem to actually figure it out in an explicit way. And this has really not been done before. This would be a very interesting research project to follow through on that. Okay, this was established quite a few years ago by me and Ogilvy and Jones and Milton and so on. But this is a special opportunity to maybe begin to understand what the C operator is. Just a comment.
Yeah, thank you. Thank you for the next comment.
Philip.
Yes, I have a follow-up comment to Carl. My colleagues constantly tell me that the lambda 5-4 theory with positive lambda is a trivial theory. So the question is, if the minus lambda 5-4 theory is not trivial, which is, I think, what you're going to show, then how could there be a bridge between them? Unless that bridge itself has a discontinuity.
Philip, I would guess that transformation is a singular transformation.
Yes.
Okay. But that's a very complicated, difficult. I don't think we should discuss that here.
No, I'm just raising it as a concern. Yeah.
Yes.
Okay. Thanks for the comments. And okay. Let me continue. So this series is a symptotic series. So if you naively sum them up, they actually just it is just a divergent. But you can actually do the Borel summation and you obtain a final result. The result is that this after Borel summation, the result actually is analytic on a cut complex plane. There's a cut on the negative axis. This is a lambda complex plane. So, and then in our work, we made this conjecture. Maybe the partition function, the PT-symmetric, the partition function for the PT-symmetric minus G5 theory is related to the Hermitian partition functions, but evaluated as slightly above the negative line axis and slightly below the negative axis. This is kind of regulator, and then we will discuss some motivation for this relation below. But before that, actually, we can see a immediate consequence of this conjecture. So this, because the energy is actually related to the Euclidean partition function, and this relation then actually implies this relation between the energies. Right? And now you can, together with another equation, this equation, first you consider this equation for a real and a positive lambda, okay? And this is valid for the real and a positive lambda, and you analytically continue lambda to minus G plus I 0 plus. Then you can show that this quantity, the Hermitian energy evaluated as minus G plus I 0 plus, has a imagined part, which is precisely the opposite of this quantity. It means that the imagined parts of these two terms will cancel out, and their real parts are the same. So this assures a real energy spectrum for the PT-symmetric theory. So if this relation is correct, then at least we can know that there must be a stable ground state for the PT-symmetric theory. I mean, because any eigen value should be real. And as we said, in the past integral formulation for formulation, there's no big difference between quantum mechanical problem and quantum field theory. So,
we have a few questions. Uwe first.
Yeah, hello. Little question. Is it ensured that you don't have any additional structure on the complex plane on the G plane? so that you can move there smoothly. Do you have, is this a completely entire function in this part of the plane, and you have only the cut, which is selecting some kind of Riemann surface structure, or do you have additional points there that might yield additional obstructions there? I'm just wondering, it's just a neutral question.
Yeah, I mean, so from my understanding, there's only one cut, but I mean, this is from the famous work by Band and Wurm. Perhaps Carl make.
Okay, I will have a more.
I can make a comment on it if you like. It is rigorously true that there are no singularities in the cut plane that includes the positive real axis. Okay, there are absolutely no other singularities except at infinity.
Okay.
Okay.
And
however,
this essential singularity at infinity, actually.
Yes, that's right.
Okay.
However, so the cut is on the negative real axis, and if you go through the cut, you can go around 3 times and you will come back to the original, to where you started. Okay, in other words, the cut behaves naively like a cubic root, like a cube root. Okay, so it begins as a 3-sheeted Riemann surface. However, the non-trivial part is this: if you go through the cut either in the clockwise or the counterclockwise direction, that is, if you go counterclockwise and you reach 270 degrees, okay,
yes,
or if you go in the clockwise direction and you reach 810 degrees, okay,
yeah,
then you find a massive collection of square root singularities.
okay.
An infinite number of
number?
singularities, and
It's
those singularities have a limit point at the origin. There are an infinite number of such singularities, and that is where level crossing occurs.
Yeah, okay.
However, again, it is rigorously true that on the principal sheet, that is on the sheet, the sheet, and this is an infinite Riemann surface, okay?
Yeah.
But on the principal sheet, which is what you see in this transparency,
Yeah, sure.
there are no other singularities except for the cut.
Okay. So all the singularity structures entering through this essential singularity at infinity, actually, which is producing this highly monodromic structures and all these additional.
There's actually, well, you can, I mean, there's an essential singularity at 0. And the essential singularity is that 0 is a limit point of square root type branch points. Okay, but they're not on the principal sheet. Okay.
Yeah. Okay. And it's in your paper with TT-Wu from 73.
Yes,
okay,
it goes all the way back to that. Yeah.
Yeah, I will check it carefully again. Okay, thank you for this comment.
Frida next, and then Sandra.
I just want to make a comment. If you exponentiate your conjecture, you obtain somehow a product of 2 different generating functions. And this is how I obtained the path integral formulation for this Nakanishi oscillator, which gives the Klein-Gordon theory for complex mass. So I had generating functions for the complex mass Klein-Gordon equation, and I had an additional term in the Lagrangian for the complex conjugate mass and the complex conjugate oscillator frequency and complex conjugate coupling constants. And so my path integral is a factor, a product of the causal theory and the anti-causal theory. So I have complex fields and the complex conjugate field, so 2 degrees of freedom. So in a sense, you have here the logarithm of this theory written down.
Thanks.
Sandra.
Yeah, one of the important things about PT-symmetric theory is that you have phase transitions. Okay, so you also get complex energies. But if you do this, then you're guaranteeing yourself real ones. So aren't you throwing away part of the physics?
Well, I mean, originally you start, so PT phase transition is usually, if I understand, for example, you start with Ix to the epsilon and times x squared, and you change epsilon there. But here, I'm not sure we have a PT phase transition with a fixed theory, but changes coupling. So as I said, for the quantum mechanics problem, we know that this theory has a real and a positive energy spectrum. So
Yeah, that's correct. So I mean, for this particular theory, it looks fine, but it just bothers me if I'm thinking generally.
yeah, generally, I think for in general case, maybe we may not have this relation, maybe it's some more complicated relation, or I don't know, and then for which you can probably see PD phase transition.
Thanks.
Frida again, and then Joshua.
Yeah, hi, just in connection to what Sandra just asked, I think all it means, I mean, I will have more comments to say later on, but as for Sandra's comments, I think all it means is that in a PT-symmetric theory, the characteristic polynomial of the differential operator here has real coefficient. That's all what it means. So either the eigenvalues are real or come in complex conjugate pairs. That's all.
Oh, I see. Thanks.
Maybe a comment to Sandra. In my theory, I have on one hand complex eigenvalues for the causal theory. On the other hand, I have complex conjugate causal, eigenvalues for the anti-causal theory. And there are special eigenvalues which are for states which are PT-symmetric. So they are real because you have a product of wave functions for the causal and the anti-causal wave functions in an equal setting. And here you see somehow the part of the phase integral where the eigenvalues get all real, but the fast path integrals produces more structure than you can read here.
Thanks, Frida.
Okay, so thanks for the discussion.
But I have still more hands up. I think Joshua made the point and just has the forgotten hand, and Philip has a question. So, Philip, you're up.
Yes, sorry.
Okay.
Very quick comment to what Carl said. If you take a double well potential and you set V prime of the potential equals J, a source, then the energy is a multiple valued function of J, and it has 3 sheets. And I think that's very similar to what Carl was mentioning a moment ago. So you can see the analytic structure if you add on a source and then look, how does the theory behave as in the complex source plane, which is basically how we always do phase transitions. That's the comment.
Thanks.
Frida, last comment. Then we have to move on, really.
A comment to Philip. My theory has a source for the causal theory and a source for the anti-causal theory. You do not have only one source, you have 2 sources. Yeah. So this makes a difference.
Okay.
Okay.
Please
So
move on now. Yeah.
yeah, I think I need to move on. Yeah, thank you for these discussions. Okay, so this is a very simple relation, and to be honest, we really do not know whether this relation is true or not, and it's so you should take it with some caveats, but we hope that this relation can provide some new way of thinking about PT-symmetric theories. And let's see some motivation first in the 0-dimensional case. So in 0-dimensional case, we can consider the Hermitian model. So this is a Hermitian model. And we can also consider PT-symmetric model. Here, if we do the integral on the real line, then this integral is divergent. So for the PT-symmetric model, we have to use a contour like this. This is a contour. And now for these two integrals, you can actually prove that there's a relation between the PT-symmetric partition function and Hermitian partition function. Okay, there are two ways to understand this. The first one, of course, these are one-dimensional integrals, and we know exact results. So we can actually simply use the exact results. The Hermitian partition function can be expressed as the modified Bessel functions k, and the PT-symmetric partition function is expressed in terms of the modified Bessel functions I, and there's a relation between I and k. So you use these relations and can prove this relation. And this actually more intuitive picture for this relation. Okay, so on the right hand side, you look at the Hermitian partition function, and then you can see that when you do the analytic continuation, you can imagine that you are rotating lambda from positive g and just change theta from 0 to minus pi plus I 0 plus. So slightly, and so this is, so when you rotate lambda counterclockwise, so from 0 to minus, from actually positive 180 degrees, then in order to assume your integral to be convergent, you have to simultaneously rotate your x, right? So this is, you rotate x times e to minus I theta over 4. The factor 4 is due to that the different power in this term, right? So in this, for example, in this Hermitian partition function, when you do this analytic continuation, you actually try to rotate the contour original real line clockwise to here to C1. Okay, so this Hermitian function is an integral on C1, and this similarly this partition function is an integral on C2, and because the integrand has C2 symmetry, so the effect of the half simply give you some integral on half C2 and half C1. So this is why you have this relation. Now, for zero-dimensional toy integrals, we can obtain exact results. But for one-dimensional quantum mechanics problem, I mean, for the real path integral, we can not obtain real exact results. So in this case, we have to search for alternative method to partially examine the relation. And then the method we are going to use is the semi-classical estimates. So here, for the zero-dimensional case, if we want to calculate the PT-symmetric partition function, then we need to define the contour in this way. Okay, this is also from the book PT-symmetry. And then we have three stationary points. So the trivial one, and also you have left. This is left and right, two types station points. And then you can calculate the integral. You can do in the Gaussian integral near the station points. Then you will see that if you do that, you will see that you can obtain an imaginary part for the PT-symmetric partition function from this line. Here we denote this line as JL, and minus because we deform into the lower complex plane. And you also obtain another imaginary part from this line. Okay. They differ by a sign. So as a total effect, the PT-symmetric partition function is real because they cancel these two. This is actually exactly an effect of PT-symmetry for the contour. On the other hand, if you look at the Hermitian partition function, and then you take g to infinity to 0, and you can also obtain real part for the for the each pieces in the relation. So you see that they are exactly the same. Means so in the relation, there's 1/2 here. Okay, there's 1/2. So exactly the same. You see the exactly the same imagined path. But on the again for quantum mechanics problem from the real path integral, we do not know the exact result. But still, we can actually derive this result using the perturbation theory, as we will show later. Now let's go to the one-dimensional case. Actually, you can see that there are some differences between the d equal to 1 relation and the zero-dimensional case. The first difference is that there are now logarithms in this relation. And the question is why there are these logarithms. The second question is how to prove this relation partially. So we don't have any rigorous proof for this relation. So for the first question, we will show that this is because there's an exponentiation in the path integral. And for the second question, so we will compare the imagined path on the left-hand side and the right-hand side, and show that they are exactly the same. Well, as I said, the imagined part cancels, so we have to compare the imagined part before the cancellation. Now let's first look at the semi-classical analysis for the PT-symmetric theory. So there, the first step is look at the stationary points. There are also here we actually consider the partition function is considered some from 0 to 0 propagator, something like it. And then you have 3 station points, not 3, but 3 types of station points. The first one is a trivial station point. You just have x not equal to 0 always. And you can also have 2 instaton solutions. So, oh, by the way, so in the Euclidean path integral, the potential is upside down. So you see that this is upside down potential. And then this particle can roll down here and come back. Similarly, the particle can also roll down here and come back. So we have 2 types, bounce type solutions. This is, so people also call it instaton. And these vectors minus g, so these vectors are precisely the station points in the 0-dimensional case. So here you see they are precisely the same. And these 2 types of bounces are parity symmetric. And then once we know the station points, we still have to determine the steep descent passes passing the station points. And so for path integral, we usually call all the steep descent passes passing a station point as a Lefschetz symbol. And the general theory to determine a Lefschetz symbol is called Picard-Lefschetz theory. In the very general case, we have to solve the so-called flow equations. But in our case, it is much simpler, and we do not need to really use Picard-Lefschetz theory. Now, so let me explain a bit more about the method of steep descent. We have a path integral, and we can define the height function. So this is just the exponent in the integrand. And then this is an example. This is a 2-dimensional example. Okay. The path CD is the steep descent direction, while AB is a steep ascent direction. In our case, the shape of the region near a station point is actually determined by the eigen equations. Well, so for the path integral we of course have infinity dimension. It's not just a 2-dimensional picture. Now, so for the positive modes, when the positive mode is just the mode with a positive eigen values. right? The positive modes give us steepest descent directions. Why? Because there's a minus sign here. So when you have positive, then it means that the direction goes down. And the negative modes gives us the steepest ascent directions. We can also have some zero modes. And zero modes actually is just some flat directions. The physical meaning of zero modes is that there are some degeneracy for the station points. So you see that actually for the positive modes, we need to do nothing. So because they already point to the steepest descent directions. While for the negative mode, we have to deform the path into the complex subcomplex plane. And in this way, we can assume the convergence of the path integral. And this is what I do. This is what we do actually. Another question is, how do we assume PT symmetry? Right. The answer is that we should correlate the deformations passing the left type bonds and the right type bonds. This is similar to this picture. Sorry, to this picture. When you deform the contour, passing the left bonds into the lower complex plane, you must also deform the contour passing the right bonds into the lower complex plane. Of course, we don't have the same complex plane for the one-dimensional case, but you have deform to the same direction. I mean, the same lower complex plane. So this way we can assume PT symmetry. No, how much time do I have? Okay, so now once we know these station points and the symbols passing the station points, then we can have three pieces of the partition functions. So these partition functions are the functions when you do some perturbative expansion around the station points. You might think that then the total partition function is just a sum of these three pieces, but actually this is not correct, because aside from this very fundamental and simple solutions, we can have some multi bounces. For example, this is X. The particle, still think about the particle in the upside down potential. Then the particle can go to the negative x axis. Then this is, you see, this is just a left bounce, and the following with a right bounce and the left bounce and many other possible combinations of these. There are also some solutions to the equation motion. So for a multi-bounce with M1 left bounce and N2 right bounce, the partition function can be written in this way. This is here the naught here is because there's the naught because we have to normalize the contribution from the trivial fluctuations. And then for the n bounds, when n1 plus n2 equal to n, then you can write the partition function as all possible combinations from here. And then finally, the partition function can be written as a trivial partition function, the perturbative partition function, and the sum over all n bounces. So you see that this gives us an exponentiation. Of course, this is just the standard picture for the instaton gas. Here I use the dilute instaton gas. Okay, and this is why now you see that there's the three fundamental pieces: the perturbative part and the left bounce and the right bounce goes into the exponent. So this is why we consider the logarithm. So we put logarithms in the relation. We know that for the Hermitian series, there's also exponentiation, right? So there are some connected Feynman diagrams. Now, now we answer that what is the motivation to put some logarithms in the relation. Then another question is how we prove this relation partially. Then we are going to calculate the imaginary part of the ground state energy. This is the formula for the ground state energy. I mean, this is the standard formula from the for example for tunneling or for spaghetti decay. And then you can do in the Gaussian function integral on the symbols on the L on here or R the symbols. Then you can obtain imaginary part for this results. Well, to calculate this quantity, you need to calculate the functional determinant, which is typically very difficult to calculate. But for our potential, because we have the very simple potential, and then we obtain exact result. And on the other hand, we can also calculate the imaginary part for the Hermitian, the ground state energy of Hermitian theory, using the Rayleigh Schrodinger series. For the ground state, we have this series, and again, this is from the famous paper by Bender and Wu. And then the coefficients an have large order behavior. Now, if we calculate the ground state energy, means a truncated n, means a finite n, then the result must be real because each term is real. So if you want to obtain some real result, we have to sum all of them. So this means that the imaginary part of the energy is not sensitive to the an means finite n. So we consider another series, but we just replace an each turn using this formula. Although for the ground state energy, this formula is valid for large order n. Okay, and then we have the same series with an here, just replace the sign to equal sign, and now then you can obtain the result. Here we use because there's a gamma function here. Then you use the integral representation of the gamma function in the summation of series, and then finally can write the series as an integral. And this integrand has is singular on the real axis. So if you take lambda to minus g, so from this integral, then you obtain the imaginary part of the ground state energy for Hermitian theory analytically continued to minus g plus minus I 0 plus equal to this result. And then you take half of this result, then you obtain precisely the same imaginary path. Okay, so this is perhaps our partial support for this relation. Finally, we give our conclusions. So in this work, we proposed a conjectural relation between the PT-symmetric -54 theory and its constant Hermitian theory via analytic continuation. And in our work, only the quantum mechanical problem was studied, but we believe that the generalization to higher dimensional case should be possible because the path integral, the path integral formulation is very general for quantum theories. And we emphasize that a rigorous derivation of the path integral formulation of PT-symmetric series from first principles is still needed. And at last, we hope that even the conjectural relation turns out to be invalid. The work itself could still provide a new way of thinking PT-symmetric series. At last, thank you very much for your attention.
Thank you very much, Wen-Yuan. Thank you. Questions, comments, Philip?
Yes, Well, thank you for a very interesting presentation. I have two very general comments. One is related to some of the discussion we had when Sandy gave her talk a couple of weeks ago. And that is, if you have an action which is PT-symmetric, is it guaranteed that there is some contour in the complex plane for which the path integral will actually exist? And I think, I don't know the answer to this, and I'm not sure that there necessarily would be a positive answer. And that, unless, I think if you can't answer that question, you can't really give a rigorous definition of the path integral formulation. I mean, you can discuss the question of whether the path integral exists as a question in and of itself, but then a totally different question is it related to a matrix element of some time-ordered product of fields? And that's a much deeper question. And there, the issue that you run into is related to something that I just published only last week. And that is that when you have the assumption to derive the path integral formula, you put in intermediate states and you assume that the sum on nn is equal to 1. But that presupposes that the states are normalizable. And that's buried into the analysis. And so I decided, well, can I find a way to discover whether the states are normalizable? And that brings us back to your very first comment, is how do you write a Schrödinger equation in a quantum field theory? And I've come up with an actual solution to that. And if I can just state it very quickly, when you have a field, you can expand it in terms of A's and A daggers, and you can write the Hamiltonian as a function of A's and A daggers alone, because the Hamiltonian is already an integral of the energy momentum tensor. When you've got A's and A daggers, you can write Q is A plus A dagger and P is I A minus A dagger. And you can therefore write the Hamiltonian as a function of P and Q. These P and Qs have got nothing to do with the ordinary P's and Qs, but they obey P comma Q is IH bar at every momentum state. And therefore you can represent them as a differential operator. And therefore you can write a Schrödinger equation for a field theory as a differential equation. Now, of course, phi-4 would mean P to the 4, which would mean 4 derivatives. So they're not very easy to solve, but you can, in principle, write down a differential equation for the eigenvalues of the Hamiltonian of a quantum field theory. And that was the result that I just wrote up last week. Okay.
Thank you. Very interesting comment. But I was wondering, so in quantum field theory, the Schrödinger equation is actually a function form. I mean, so it's not just a ordinary differential equation, right? Or...
Everything you said is correct. And for the whole of my career, I believe that to be the case. However, that's because you try to represent the commutator of phi with phi dot as a delta function. You try to represent it with phi dot being a functional derivative with respect to phi. That's the way it's done in quantum field theory. And that is a very nice formalism, but it makes it totally hopeless to determine eigenvalues. Mm-hmm. But what I realized was that nonetheless, the Hamiltonian can still be written in terms of creation and annihilation operators. Mm-hmm. And therefore you can convert that equation, that Hamiltonian, into a differential operator. And there, I mean, my own interest in doing this was because I wanted to check, as I said at the beginning, is it really true that the norm of these states is finite? And the answer in the examples I looked at, the answer was no. You see, so if you ever do field theory, that's your job, and this is the job of every field theorist, is to show first of all that the ground state has a finite norm. Mm-hmm. And that's the challenge. And just one other comment. The reason why it relates to PT is if the norm of the ground state is not finite, the path integral does not exist on the real axis.
Mhm,
but it might still exist somewhere in the complex plane.
mhm.
And that's how we tie everything together. Okay.
Philip, you could have given a talk next week. I mean,
Well, that's up to the organizers. I'm
but to
No,
verify.
Philip, sorry, Joshua. We sent out a call some time ago. Anybody who would like to speak can speak. If you
Okay.
want to talk.
all right. Well, the situation was when I received the call, I didn't have anything to say.
Okay. But it's still open. The call is still open.
In that, yes, I would be very happy to talk about this.
Very good. Let's communicate together.
Okay, yes.
So, yeah. Joshua.
So now I don't know what to relate to Philip's last comment or to the talk itself. So let me start with the talk itself. So thank you again for your talk. Now I have a very basic question about applying this path integral formalism in PT-symmetric cases. In particular, those minus phi to the n, ig phi to the n kind of theories. So what exactly, and it relates to Philip's one of Philip's questions. What matrix element actually are you computing? You write a symbol, sum over all field configurations in the complex plane, and you make sure to run in the correct wedges, Stokes wedges, etc. But what actually are you computing? Which matrix element of the field theory are you computing? Are you computing the Feynman propagator? Are you computing the coefficient function? What is it that you are computing?
Yeah, so actually, I mean, so we already discussed the quantum mechanics problem, and so for the quantum mechanics problem,
yeah, my question is valid there as well.
Yeah, that's right. So for I just want to explain this using what we did. Actually, for the quantum mechanics problem, we actually the partition function is actually specifically to the 0 x equals 0 propagated to 0 itself, means a large Euclidean tie. So this is
how do you know that? How do you know that? I mean, in order to validate what you say, you have to diagonalize your operator. I mean, the X operator, which is not an observable in this case. So
that's right.
You assume it's diagonalizable, and you assume that you can create generate a resolution of unity from the right and left eigenstates of that operator at each time.
Yeah. I mean, this is actually the here I decided why I call it assumption and why I highlight this in red.
Well, I've written a paper with Fabio a few years ago where it's not an assumption, where it was actually a construction. And there we managed to do the path integral properly for the Swanson, one of the versions of Swanson's model. And there we showed that in order to compute the Feynman path integral, you really, I mean, we did it both for coherent states and also in terms of X and P. And there we made sure that indeed our matrix element was the correct propagator. I mean, it starts from a delta function at time 0, and then it evolves to whatever it needs to evolve to. So and also when you in the business of calculating physical elements, you really need to include the metric as well at one of the boundary points. So so here there was no, it was completely unclear what you're doing in this sense. So can you I don't know, comment on this? Or you have written assumption, and in the third point that you mentioned in your conclusion, you said that rigorous derivation is needed, and I couldn't agree less. I couldn't agree more with that. It's the obvious thing. So what do you think you should be, what should be done in order to fulfill this goal?
Well, so I think this is a very hard question to me. I mean, I'm not sure I understood your comments very clearly. So you mentioned that you did some work and then you derived the path.
No, my work is not important. What is important is to have a clear picture what you are doing. So when you write a path integral, it means you are summing over trajectories in some complex configuration space. Why are you doing this? And what is this sum? What does this sum lead to? I mean, which matrix element does it compute?
Yeah, as I said, the elements we are calculating.
Yes. In point three.
Yes.
The Hermitian case, right?
Yes, this is a Hermitian case, and then, as I said, I currently I do not have any idea how to, rederive path integral for a general PT-symmetric theory. And even though for G-54, as commented, for this special theory, there might be a way to actually derive the path integral because we know all the C operator exactly, right?
Well, the C operator will be relevant only to the endpoint. I mean, you can just calculate the matrix element between two x's, but it won't be the proper Feynman propagator.
Yeah. In general, I don't know. We have to properly define the position eigenstates and moment eigenstates. I'm not really sure. Yeah.
Maybe I can comment to Joshua. We do path integrals backwards. We start with the matrix element and derive the path integral. But there's a different way to do it. Start with a classical theory. Do a variation over the classical paths to find the stationary minimum. That's straight Euler-Lagrange.
Yes.
Now do an integral back over that same set of paths. And that defines your path integral. Then the only issue you raise is there a way of making that integral exist? If it does, then it will correspond to some quantum field theory, but you don't know a priori what vacuum or what fields you're looking at. You hope, and if PT symmetry is the most general thing, you hope that it will be the one vacuum, the right vacuum, and the left vacuum will be the PT conjugate of the right vacuum. That's what you'd like to have happen. And if that happens, then it's wonderful. But whether it will...
Physics and hope go together. That's nice.
Well, the hope that when you integrate back over you see, when you did the variational path variation, you found a set of paths. You now hope that when you integrate back functionally over that set of paths, that you get something meaningful.
Yes.
That's the, if you don't, which is the big concern, then you can't simply say, oh, this is some quantum field theoretic matrix element.
But what are the paths?
And for me, that's the big dilemma of path integration. Is you never ever do specify a Hilbert space.
Well, in the Hermitian theories, you always have
There's no reference in a path integral to Hermitian. There's nothing in a path integral that says anything about Hermitian, and it says nothing about Hilbert space.
No, but in order to connect your path integral to some physical realistic, some physical reality, you need to connect it to some Hilbert space, to some. You calculate probabilities. You calculate matrix elements.
Then you come back. Then you come back to the original question. The original question is: you write down an action, vary with respect to the fields over some set of paths that you may not specify, and you get an equation of motion. You now impose phi dot is a delta function. Where's the Hilbert space?
Well, if you impose phi dot as a commutation relation, it means you are dealing with operators. And
yes, but
operators
you still haven't
are in the algebra acting over some Hilbert space, no?
No, you haven't specified a Hilbert space when you specify a commutation relation.
Yeah, but if you have a well-defined physical problem, then it's not a matter of hope. It's a principle that it should be involving some decent Hilbert space. No,
Maybe I may contribute to this discussion, because I think it's turning in a circle. I told you I had this causal part of quantum field theory, which has functions of the variable z, so holomorphic functions, and anti-causal part, which has anti-holomorphic functions in the variable z bar. Now, if you look here on the screen, you see these matrix elements between xf and xi. So in my case, this is not a matrix element between xf and xi, but the final state is defined by a variable zf and zf bar, and the initial variable is defined by zi and zi bar. So it factorizes it in integrals, where on one hand you insert here these completeness relations, where you have the integrals dz, z bra and z cat, and integrals over z bar and z the respective brackets for the z bars. So you have two variables, and this leads to the fact, Philip, that you have normalized state in the variable z, and you have normalized states in the variable z bar, and the whole is a product of both. So you get a product of two phase integrals, one for the causal states and one for the anti-causal states. So you have two sources, and by deriving your phase integrals or your generating functions by these two sources, you can obtain causal green functions or anti-causal green functions. And if you take a suitable linear combination, you get acausal green functions. So PT symmetry in the whole game is that a PT transformation interchanges the holomorphic functions and the anti-holomorphic functions. So you interchange the causal sector of the theory by the anti-causal theory. And I return what I said to Ms. Klevansky. In the causal sector, you can obtain arbitrary complex eigenvalues. And in the anti-causal sector, you obtain the complex conjugate eigenvalues. And by taking a certain combination in your wave functions, you can go to the special case where you have real eigenvalues. And the minus lambda x to the 4 theory, it's in principle a theory which fits completely in this game. Yeah, so you have a Hilbert space, but it's living in two complex planes. In one, which is a complex plane Z, and in the other, which is the anti-holomorphic complex plane Z bar. And you have integrals over Z and Z bar. Yeah, and so it's very simple. I did this by canonical quantization, and I obtained exactly as Philip said, creation and annihilation operators, but these creation and annihilation operators are not Hermitian conjugate to each other. They are PT-symmetric to each other.
They should be, yes. They should be PT.
And this leads in such indefinite metric. The only trick is to preserve in quantum field theory Lorentz covariance. If you allow the causal and the anti-causal operators to interact, you somehow destroy everything: locality, causality, and Lorentz covariance. And Nakanishi was throwing away his theory because he thought this is a bad drawback of all this game, but it is not. The only thing is I can calculate with these Green's functions and with these path integrals amplitudes, but to convert these amplitudes into probabilities, this is another trick, because you have, by these Green's functions, you get somehow the classical, you can get coherent states which move your particle classically in the complex plane. But the problem is with these matrix elements, you cannot really calculate probabilities in the standard sense. You need to construct a different probability matrix elements to obtain probability. Usually you take imaginary parts of Green's functions or to calculate cross sections and all that. You have to extend your quantum field theory to these things. I mean, I have written this nearly up, but I am not finished with all that. If there's a time, Andreas, I could give a talk on this, hopefully before August, but I think this will settle this confusion.
Okay.
Well, you're very welcome.
That's a very, very nice analysis. The only question I had is the one I raised before, and that is, you write down, even with the z and the z bar, you still are writing down a completeness relation, like the integral dx xx equals 1, presupposing that the states are normalizable. And I completely
They
agree.
are indeed,
No, I mean,
because you
I
get
agree with you completely that if they're normalizable, then everything goes through. The way you
normalizable in which sense? In which sense normalizable? To
whether,
delta?
not renormalizable, that the vacuum, that the state, the norm of the inner product, ket bra n ket n is finite.
But
in quantum field theory, you get delta.
if you use x and p, I mean, it's not normalizable. It's delta function normalizable.
No, that's not what I had in. That's not the issue that I had in mind.
You have two representations. You have the spectral representation where it's finite, and if you make these completeness relations in the integral of on z, somehow you have delta functions in the complex variable z, and you get wave functions which are somehow, when you perform these integrals with suitable contours, giving finite normalizations. And this goes completely through.
Yeah, look, one of the ways that you derive the Layman representation, one of the things you need for the derivation is the normalizer, is that the matrix elements are finite. Yeah. It's part of the construction. That's the only question that I'm raising. And that's what I will let Andreas and Francesco know about. Maybe if you have the patience, I could even discuss it. But that's the question I'm raising. It's such an obvious. It's so obvious that it was never thought about. Namely, is it so obvious that a Dirac inner product is finite? And if it's not, then none of the standard discussion works.
But Philip, the inner product of those field theoretic states is by itself a path integral, no? The inner product of two wave functionals that you are saying, or the norm of the vacuum.
I'm being very, all I'm saying is the following. You construct a Hamiltonian as the integral d3x of t00. You impose the field commutation relations and you get an expression for a Hamiltonian.
Yes.
It has a vacuum that the A's and the A's annihilate. Is the norm of that vacuum, namely vacuum expectation value, is it finite or is it not finite? That's what I'm asking. Now, if it's not, then of course matrix elements of products of fields in that same vacuum are also not finite.
Yeah, but then there are those subtle questions. Let's look at each. I'm sorry, we are now doing an.
How about Philip?
Yeah.
Philip, how about you give a talk next week?
Yeah.
Next week.
Is that too quick? Is that too soon? But it would be a nice follow-up. How about that?
Just give me 10 seconds. Thursday the 16th, that would be fine. Yes.
That's right. That's right. That's next week.
Okay. Yes, I can do that.
Okay.
I will watch the recording because I will be busy.
Oh, sorry.
Okay.
Oh, okay. Anyway,
Okay, then this is settled. Maybe we have another discussion then about these general points. Yeah.
Yes.
Yeah. So Wen-Yuan, you have the last word. Maybe do you want to add to this discussion?
Not really. I mean, so actually, I'm not. So
Okay. Okay.
Okay. I hope you are not traumatized by this onslaught of the elderly.
No. He's done very well, and he's led us. He's given us his work, and it's clearly opened up lots of interesting directions, which is just what you want. So thank you for that.
Thank you.
Thanks again for the talk, Wen-Yuan. Thank you.
Thank you.
And sorry about the delay.
No,
for
no,
everybody.
No, it's
fully.
Okay, everyone, bye-bye.
Okay, bye. So
Bye-bye.